Okay, so they want us to determine the PCA for this particular data set. The first thing is I want us to clearly define our x1 and our x2. So x1 is going to be equal to 2, 3, 5, 8, 9, 10, while our x2 is going to be equal to 92, 100, 89, 78, and 65. Now the first thing you want to compute is the mean. You will see why shortly. So the mean for the first set is simply going to be add up everything and divide by 5. It's going to give you 56. And the mean for the second one, add up everything, divide by 5. It's like normal average to give you 84.8. Sorry, this is 5.6, not 56. Now I'll simply write it in vector form. It will be 5.6 and 84.6. Now we're going to find the standard deviation of this. So this is the first step, this is the second step. Deviation, we're going to be using sample standard deviation. There's population standard deviation and sample. We're going to be using sample. It simply says the summation of x sample features minus the mean square over n minus 1. That's why I say we need to find mean. So I'm simply going to put this in a table for clear confirmation of what we are doing. So this is going to be x minus x bar. You can use your calculator. So it's going to be 2 minus 5.6 minus 3.6. So I'll just write the remaining. Now you simply take the square because this wants you to take the square. The square will be 12.96. You can do the rest with your calculator. And now simply square root, add up all of this because the summation is simple is here. Add up all of this, give you 45.2, and then simply square root everything. That will give you 3.36. So the standard deviation for the first sample is 3.36. Now for the second sample, x2, I'm going to do x minus x bar. In this case, it's 84.6, so 92 minus 84.86 is simply going to be 7.2. The remaining, and now I simply square them to give you 51.84. And when you simply add all of this, you're going to get 738.8. You square it, you're going to get the standard deviation for the second set is equals 13.59. Now you can actually just put it in the same vector form. So this will be 3.36 and this will be 13.59. Now the third step is to actually standardize your data using something we like to call z-score. So the formula for z-score is simply z equals to x, that is the sample, minus u, that is the mean, over the standard deviation. That is where we found the mean and standard deviation. So z is going to be a matrix in which the first column contains the x1 and the second column contains the data for the x2. So if you remember, these were values. So this is going to be 2 minus, what was the mean for this one? The mean for x1 was equals to 5.6 and the mean for the second one was actually equals to 54, no, 84.8. Standard deviation for this one, 3.36. Standard deviation for the second one, 13.59. It's going to be 2 minus, what is its mean? 5.6 all over 3.36. This one is going to be 92 minus 84.8 all over 13.59. Now that's just what you keep doing for the entire data set. I'm just going to write it out because I believe you can also solve this out with a calculator. Now after you do standardization, what actually happens behind the scenes is that each column has a mean of 0 and a standard deviation of 1. So that's what happens behind the scenes after this score is done. So the next thing you want to do is you want to find the covariance of the matrix of this standardized data. So the formula for that is 1 over n minus 1 z transform times z. We know what z was. Z transform will simply be equals to minus 1.07. Okay, now we can simply multiply zt times z. Now notice that this is a 2 by 5 matrix multiplying a 5 by 2 matrix times the ultimate matrix will be 2 by 2. So to get the first one here, you multiply this row times the first column here. That'll be this times this plus this times this plus this times this. When you get your final answer, you get your final answer to be 4. To get this second point here, you simply multiply this same first row but times the second column this time. This time you will get minus 3.68. The next one is this second row times the first column minus 3.68, and this times the second column. Now simply you have to divide by 1 over n minus 1. What is n? N is equals to 5 because there are 5 sample data. So you can look at x1 and x2. You're going to be 1 c equals 1 over 4. 4 minus 3.68 minus 3.68. 4. Divide everything individually by 4. This will become 1. This will become minus 0.92. This will become minus 0.92. This will become 1. Now the next thing we need to do is we need to find our eigenvalues. So to find our eigenvalues, we're going to take the determinant of C minus lambda I. In this case, I is an identity matrix given like this, and lambda, if you multiply lambda into this, it simply make this lambda, make this lambda. Lambda times 0 is nothing. So it's simply going to take the determinant, minus 0.92. That's, I'm writing the C matrix, minus 0.92 and 1. So that's the covariant matrix, minus lambda 0 0 lambda. This is going to be 1 minus lambda, 1 minus lambda, minus 0.92 minus 0. So you just do the same for the bottom as well. I remember that we're taking the determinant of this. Go online and search for how to find the determinant of a 2 by 2 matrix. It should simply just be this times this minus this times this. So it should be 1 minus lambda times 1 minus lambda. I can just write square minus, sorry, this will result in 0.8469 is equal to 0. That's how to do determinants. So you can take this to the other side, 0.8469, and to cancel out the square, you can square it both sides. So this will leave you with equals to plus or minus 0.92. Now the first lambda is equals to 1 plus 0.92 is equals to 1.92. The second lambda is actually equals to 1 minus 0.92, which is equal to 0.08. Now notice that when you add the both of them up, it's going to give you 2. That's because the sum of your two eigenvectors, that's because the sum of your two eigenvalues must be equal to the number of feature data sets that came in. We had x1 and x2. There were 2 features. This must equate to that. Now, number 6, we are to find the eigenvector for lambda 1 equals to 1.92. The formula is given as C minus 1.92 I times V1, in which this is the unknown eigenvector. Now we know our covariance 1 minus 0 minus 2. We negating 1.92 0 1.92. We know how this comes about. Now this is going to be V11 and V12. So this is the first row. This is the first row of the eigenvector. This is the second row. Equals to 0. If you solve this, you're going to have your answer as minus 0.92, minus 0.92, minus 0.92, minus 0.92 times V11, V12 equals to 0. Now, just multiply this again, multiply in our matrix. So this first row by this column. So it's going to be minus 0.92, V11 minus 0.92, V12 equals to 0, right? Divide through with negative 0.92 to leave you V11 plus V12 equals to 0, which means that V11 is equals to negative V12. Now you can take a very small value, you can equate V11 to a very small value, is equated to 1, And so therefore v1 to be equals to negative 1. To write this is to simply be 1 and negative 1. Find the magnitude of this. You'll see why shortly. So this is actually for v1, right? Find the magnitude of this is simply root 2 because 1 square plus minus 1 square squared everything. It is root 2. Now you have to normalize the v1. So that will equal to 1 over root 2. That's 1 over the magnitude times the eigenvectors of 1 and minus 1. This will give you 0.707 and minus 0.707. And now for our second eigenvalue, was equal to 0.08, you do something, not something, you do exactly that, but this time with its own v2, that's its own eigenvector. We're finding eigenvector for it. That's simply going to be this. And if you resolve this, you're going to, well, we're just going to do this how we did the last one, 0.92 v2 divide through with 0.92 this time to give v21 minus v22 equals 0. That means v21 is equals to v22. We're simply going to equate v21 to a very small number value, and since v22 is equals to 2, it should be equals to 1, which means v2 is equals to 1, 1. Find the magnitude. The magnitude of v2 is equals to root 2. Now to normalize v2, it's going to be what? 1 over root 2 times 1, 1, right? Which simply gives us 0.707 and 0.707. These are our eigenvectors for. Now the PCA transformation matrix after everything is V equals to, this is for the first one, 0.707 and minus 0.707. And this for the second one, 0.707 and 0.707. For PC1, going to be equal to lambda 1 over the total variance. I'll tell you what the total variance is now. The total variance is simply just lambda 1 plus lambda 2, which is equals to 2 times 100. So it's going to be 1.92 over 2 times 100%, which is equals to 96%. And for PC2, it's going to be equals to lambda 2, 0.08 over 2 times 100%, which is equals to 4%. This 96% is really good. You're seeing 96% of all patterns in the data, but this 4% is mostly just like noise or minor variations that are here. So in real machine learning, we will drop this particular this thing. And I hope you understood, and please do not forget to like and subscribe.